We have some great talks lined up this evening for you about H3 and about how we're defining geospatial areas at Uber. We have Nick talking about grid systems and H3. We have Ankit and Gucheng talking about geospatial engineering and some of the backend systems that we're building to support this. And finally, we have a really interesting talk from NC and Camille about defining city cores at Uber. So with that, I'm just going to hand it off to our first speaker, Nick Rabinowitz.
Hi, thanks. So I'm going to be talking about introducing H3. And hopefully this will be a talk that'll be interesting whether or not you've ever heard of or worked with H3. I tried to give an overview, but also go in depth a little bit. So let's start by talking about just what grid systems are and why you would want one and why it's different from other kinds of geographic representations. And then I'll talk about why we chose hexagons as the basis for our grid system, why they're so great, why everyone should have them. I'll get into a little bit of depth about how we actually construct the grid system and what some of the reasons why we made some of our decisions, and then some of the challenges that you might face if you use it. And then finally, I'll give a brief tour of the H3 library. For those of you not familiar, the H3 library, by the way, is available. We built it as a C library, but it's available in a variety of languages through bindings, and you should definitely check it out if you have a chance to work with it. So geographic grid systems, what exactly are they, and why would you want one? The real world is messy. The real world has all sorts of geographic elements that are very difficult to model in most systems. It may have human-built elements, it may have natural elements, it may have things that don't follow any kind of consistent structure. And in order to do most kinds of data analysis or geographic algorithms over it, you need to come up with some more abstract version of it. And maps are probably the most common abstraction. We're all familiar with them, but they're not actually all that abstract. They have a lot of messiness themselves. Even if you take something like admin boundaries, like states in the United States, they still have all sorts of idiosyncrasies. I often think about Washington, D.C. as being like a good example here, where if you are doing state-based data and Washington, D.C. is an important data point, then admin boundaries are very problematic for you as a geographic unit. So a grid system basically takes this messy geographic space and moves it into this clean, nice mathematical space that's really useful for running algorithms, doing aggregation, having comparable geographic areas no matter where you are in the world, and being able to build other kinds of geographies on top of it, as we'll talk about today. So the first step in a grid system is you kind of break the world up into uniform cells. And these cells are your unit of analysis. You can use them in a variety of different geographic systems or approaches. They're a little bit like pixels in an image, you can imagine. You can index your data, any kind of data, to these cells based on their latitude and longitude. Then you can run algorithms over that. So in this case, we're like finding neighbors. This is maybe not quite as accurate, for example, as doing a radius lookup, but it is much, much faster. And it's a very easy way to simply see who's nearby, for example, especially if you're trying to index millions or even billions of points. And you can aggregate by cell, and then you have these cells, again, as your unit of analysis with data that's derived from the things within those cells. And that can be really useful for a variety of other applications. So that's a grid. What's a grid system? A grid system has a couple things layered on top of this. It has a series of related grids, usually. Usually these are at different levels of resolution, so different granularities. And most grid systems have increasingly fine grids down to some small amount. H3 indexes down to about a square meter. And they include a unique way to identify any cell in the system, usually through a short identifier. So a couple different grid systems besides H3, we have the graticule, so the latitude-longitude system. You can use that as a grid system simply by reducing precision. And a lot of people have used this historically as an easy way to index data. Web Mercator tiles go sort of one step further. They divide the Mercator projection into a bunch of sort of quad tree-based subdivisions. And they allow you to index things by X, Y, Z coordinates. And this is usually used for web maps. as a lookup system for web maps, but you can also use it to index data by indexing things at a particular Z level, basically. And finally, S2 is a grid system similar in some ways to H3, developed by Google, that also uses quadrilateral tiles, but does not align with the latitude-longitude grid. They have a separate way of indexing cells in their system. And like H3, they have cells at multiple resolutions that cover the entire globe. And so finally, that brings me to H3. H3 is the grid system that Uber developed with a hexagon cell as its base. And we use this to cover the world and index things at a variety of resolutions, from the top level cells that are approximately continent sized to the finest cells, which, as I said, are about a meter squared. So basically, any kind of geographic data you want to index, we have a resolution that's probably roughly appropriate for it. So why do we choose hexagons? One thing you can see from all the other grid systems is they all use quadrilaterals or squares, and those have some good properties. But hexagons have some great properties that we really like, and usually there are trade-offs between them. And this is probably one of the most common questions that people have when they're asking about H3. Now, there are a lot of tiling options if you want to make a grid cell. Why do we choose hexagons instead of, say, fish or birds? So if you're actually starting off with this, reductio ad absurdum with the fish and the birds, you can see that there's some things that you might actually want out of a cell. There's some properties that you might find more or less useful. So some properties that you might find more useful include uniform shape, uniform edge length, uniform angles. These all help to make the cells more comparable across the globe. They also mean that things within the cell are more likely to be close together than they are far apart. You can imagine if you have stretched out cells, then the things within those cells might be far apart from each other. And that basically leaves us with only the three regular polygons that can tile the plane: equilateral triangles, squares, and hexagons. And each of these are possible bases for a geographic grid. Of them, the hexagon is the most compact and the best at space filling. So if you need to take a polygon, fill it with cells, you'll get the least error with hexagons in general, on average. Squares and triangles have different properties in this. Triangles are probably the worst in these particular properties. The other big thing that we care about a lot for a variety of algorithms is uniform adjacency, which basically is how unambiguous are your neighbors. So squares have 4 unambiguous neighbors, but they also have these 4 ambiguous neighbors at the corners. And you might have points that are very close together at the corners, but are maybe or maybe not in neighboring cells, depending on how you want to define it. The story for equilateral triangles is even worse. You have 3 unambiguous neighbors and 9 ambiguous neighbors. And this is about the point in the talk where I stop talking about triangles, because this is one of the things that makes them a very poor choice for a geographic grid system. You can also see from this that when you do grid out things in triangles, you have to flip the orientation for every neighbor. And those two things between them usually keep most people from using triangles for grid systems. Hexagons are a much better story here. They have 6 unambiguous neighbors. Each of these has the same property, and that makes them very good for modeling any kind of flow between cells, for doing a variety of algorithms where you're trying to traverse neighbors. For example, if you want to find things by radius, hexagons are a really good choice. It's not an exact radius lookup, but it's a lot closer than it would be with a square. Another thing you really want in a shape for tiling in your grid system is hierarchical relationships between resolutions. So for squares, this is a really easy story. You can subdivide a square into 4 children. You can use quad tree algorithms to go up and down and to index things. And you have a nice sort of relationship between the parent and the child. In particular, you have this perfect child containment. So everything within a child is guaranteed to be within the parent. Hexagons don't have quite as nice a story here. They do have an option to have a hierarchical relationship with their children, but they don't have perfect child containment. You can't make a big hexagon out of small hexagons. So what you can do is you can assign these 7 children to the parent and have a fixed margin of error between the parent and the child. So if you're willing to live with that margin of error, this can work just as well for your hierarchical system. And finally, you want low shape distortion and low area distortion. And if you know GIS, you know that this is actually a function of your projection usually, rather than being a function of the shape you're using in the tile. there are different ways to do, well, there are many, many different ways to do projections. Most geographic grid systems are based on polyhedra, and some of them are based on cylindrical projections. So the cylindrical projection works well for something like Webb-Mercator. It works really well for squares because it can flatten into a rectangular shape. But it has this problem of huge distortion toward the poles, and it's hard to get equal area and equal shapes across the entire projection. The various polyhedra, and these are the five Platonic solids, which are the five polyhedra that have regular faces, that all have uniform faces. These are usually pretty good candidates because, again, you have the same properties of having a uniform face, similar to uniform tiles. You have things that are easily comparable and that work the same across the grid system. And the smaller the face, the less distortion you have. So if you're using a polyhedron for your projection base, you can make a different projection on each of the faces of the polyhedron, and you can get least distortion possible. The icosahedron, which has 20 sides, that's the one on the bottom left, it's the best option in this case because it has the smallest faces, and therefore the least amount, you can have a projection that has the least amount of distortion per face. You will see that it's hard to fit squares on an icosahedron. It's hard to fit squares on a tetrahedron. You can really only fit squares on a cube without having these really nasty problems at the edges. You can fit triangles really well on octahedrons or on icosahedrons, but you can also fit hexagons, as we'll see, because hexagons can be decomposed into triangles. So just to review, we've got the square as one of our top candidates. Squares are, they have a lot of good properties, especially the perfect child containment, but they're not great for being optimally compact. They're not great for being space filling. And they don't have uniform adjacency. And so for a whole variety of algorithms, especially ones that Uber happens to be really interested in, that's a big problem. And then it's also hard to get low shape distortion in a lot of cases. Hexagons have this other set of properties, and the big trade-off here is that we don't get perfect child containment. But for almost everything else, with the possible exception of uniform shape, which I'll get to in a sec, hexagons are actually a really good choice for a grid system. So how do we build the H3 grid system based on this? We've now chosen our base polyhedron, the icosahedron, and we've chosen hexagons, and we think that that's a good combination. How do we put these together? So we take the icosahedron, we project it on the surface of the Earth, and then we take each face of that icosahedron and we split it up into the hexagon cells. So you get 4 cells that are completely contained by the face. You get 3 cells that are half contained by each face. And then you get these corners that I'll talk about in a second. And then given that initial layout, these are called our base cells in H3, you can then subdivide and subdivide and subdivide to create the lower levels of the grid system. So each hexagon gets subdivided into its 7 children, that gets subdivided into its 7 children, so on and so forth, down to the meter level. And that gives you this globe-spanning grid system. Again, these are the base cells. And gives you a pretty good way of laying out base cells anywhere on the globe. There's a couple choices here that are kind of important. One choice is the layout of the icosahedron. You can imagine you can orient that pretty much anywhere you want toward the globe. We have chosen to use a layout developed by Buckminster Fuller called the Dymaxion projection, Dymaxion layout. And the benefit of that is that all the vertices end up on water. So you can see, again, this is a little bit Uber-centric, but probably useful to a lot of other folks as well. We care more about land than water. And so if you don't have to deal with the pentagons as much because they don't show up a lot in your work because you're very rarely working on water, then that's a big benefit. There are other layouts that have other benefits with regard to their orientation toward the poles or the equator, but this is one that worked really well for us. Now, the astute observer will notice some problems here. Specifically, there are all these pentagons. And we said we were laying this out with hexagons. So what exactly is going on there? The issue, of course, is that if you look at the icosahedron, you have 5 faces coming together at every vertex. And when we kind of truncate that to create the base cell, we end up with a slightly unavoidable pentagon. In the H3 world, we like to think that a pentagon is just a hexagon that's missing one of its axial coordinates. But they do cause a little bit of problems in some of the algorithms, and we have to work around them at times. It helps a lot that there are only 12 of them at every resolution. So at res 0, you have 12, and they're really big and might be like something you really have to pay a lot of attention to. At res 9 or so, when you're dealing with like city block size, the pentagons are way out in the water. You almost never have to deal with them, and you can safely ignore them. So now we'll talk about building the actual index, which is the unique identifier for a cell in the H3 system. So the cell is identified by a 64-bit number, usually represented as a hexadecimal string. That's what's shown at the top here. We basically take those 64 bits and use them as well as we can to fit all the information we need for the cell. So we have a mode bit that, probably 2 bits at least, that indicates which mode we're using. Mostly we're using the hexagon mode, but we also have a separate mode, for example, for edges, where you can uniquely identify an edge as well. We have the resolution of the cell. We have the base cell out of the 122 base cells that we laid out in the beginning of constructing the grid. And then we basically just have the index 0 through 6 of the child at every single level. And so you can index all the way down. We have 15 resolutions primarily because that's how much we could fit in 64 bits. And so you keep on going and subdividing, and you can get all the way down in the single index. You can uniquely identify a very small geographic area. And 64 bits is a pretty good size for data transfer and for dealing with, you can usually deal with it as an integer if you are lucky and don't use JavaScript, or if you're using JavaScript, you can use the string. So I'll give you a very brief tour of what we've actually built in the library. And again, the library is written in C, but it's available in Java, JavaScript, Python, Go, and a bunch of other ones that have been contributed by the community. So the core functions are those that allow you to find out where a point is in the grid and find out where the grid is in geographic land. So geo to H3 takes this point and tells you what cell it's in. H3 to geo does the opposite. It takes a cell and tells you where the center of it is in geographic coordinates. And H3 to geo boundary gives you the vertices of the cell, which is really useful if you need to transform it into a polygon for using it in other kinds of geographic systems. The k-ring function and its friends are largely about traversal. So the k-ring finds all of the neighbors within a distance k from a given origin. And this ends up being really useful for a variety of things. For example, if you think about buffering some space, you can just take the k-ring for a certain distance around every cell in your group of cells that you want to buffer, and now you have an expanded set of cells. It's also really good for smoothing algorithms because you can take some function and decrease it by every k, and find those through the k-ring algorithms. We also have a line algorithm that allows you to draw between an origin and destination and get a line of contiguous cells, and a distance that gives you the cell distance between two things, between an origin and destination. And then finally, we deal a lot with regions, and that's the subject of a lot of the other talks here, where we're defining geographic areas as sets of H3 cells. And that gives you a lot more latitude to define more complex areas than just a hexagon. So polyfill allows you to go from a polygon to a set of H3 cells. We've chosen to implement this by taking the center of the polygon and any polygon whose center falls, center of the cell. Any cell whose center falls within the polygon is included in the set. This means that you usually don't fully contain the polygon or vice versa. But the nice thing about it is that if you have a bunch of contiguous polygons, for example, a bunch of administrative areas, and you transform them into H3 sets, those H3 sets are now contiguous. And that ends up being a really useful thing when you need to go back and forth between polygons and sets. And then H3 set to multi-polygon is the reverse. You take the set of H3 cells and you return the bounding polygon. And this allows you to use H3 in a variety of systems that don't necessarily have H3 as a primitive. You can transform it to a polygon, use it in whatever system you want that has to deal with polygons.